Okay, for the week 3 of Mathematical Foundation for Industrial Engineering, we will talk about computer number representation and roundoff. There are several agenda for this topic, which including these 10 topics, subtopics, and we will discuss this one by one. Okay, numerical methods in which the general topics of our class are a set of techniques for solving mathematical problems using numerical approximations. These methods are used to approximate solutions to problems that cannot be solved analytically, or for which an exact solution is difficult to impose to or impossible to obtain. And numerical methods are a procedure that allow for efficient solutions of a mathematically formulated problems in a finite number of steps within an arbitrary precision. So, when we talk about precisions, although that scientific calculator can handle simple problems, computers are needed in most cases. Therefore, numerical methods commonly consist of a set of guidelines to perform predetermined mathematical or algebraic and logical operations leading to an approximate solution of a specific problem, such we also known as an algorithms. Since computers were involved, therefore we need to understand how computers were representing numbers in their systems. In numerical analysis or numerical computations and scientific calculation, a significant figure, also known as digit, is a digit in a number that carry meaningful contributions to its measurement resolutions. Okay, this includes exact leading zeros, which do not affect the value of a number. For example, let's say you have 0.0034, so you will consist that it only has two significant numbers. Another things that is not included in significant figures were trailing zeros. For example, if you have 34,000 or 3,400, so the trailing zeros were not significant. This also we consider that you have two significant numbers. So when performing calculations with numbers that have different number of significant figures, it is important to keep track the significant figures to ensure that the final answer is expressed with the correct level of precision. So here's we have an example of an automobile speedometers and odometers illustrating the concept of significant number. When we see that the needles that show in which the current speeds are currently on were showing a number between 48 to 49 kilometers per hour. So if you want to be precise with the measurements, we need to really think in how in what precisions those measurements want to be reported, and then based on that report of measurements, we can select how many significant numbers were involved over there. Listed here are the basic of laws considering significant figures. First of all non-zero digits normally are significant figures. Zeros between non-zero digits are significant. Trailing zeros are the most right. Zeros are significant when there is a decimal point in the numbers between that just after those trailing zeros. Okay, another things we're talking about precisions and accuracy. Accuracy and precision are two related but distinct concepts in measurement. Accuracy refers to how close measured value is to the true or accepted value. For example, if you are measuring an instrument which is calibrated and give a reading of 10 grams, when the true weights were 9.9 grams, for example, we can call these instruments were accurate because it's very close to uh, the true value being measured. And then precisions is the degree of reproducibility of a measurement. For example, if you measure a measurement is said to be precise if it is given the same result multiple times when measuring the same quality. For example, if you are measuring an instrument reading of 10 grams and then you have 10.01 and then 9.99, we can call this measurement is quite precise because they have the same weight 3 times in a row, almost the same measurements in 3 times in a row. A common way to represent the difference between accuracy and precision is through the use of target diagrams. For example, these diagrams, each point represents a single measurement, and the distance from each point to the center represent the deviations of the measurement from the average of all measurements. If all points closely grouped together but not near to the center, for example, figure number C here, we call that the measurements are precise but not accurate. So they have high precision but low accuracy. If all points are closely grouped around the centers, the measurements are both precise and accurate. For example, measurement number D here. To sum up, accuracy is the ability of measurement to match the true value. Meanwhile, the precision is the ability of measurements to be consistent. A measurement can be precise but not accurate, or accurate but not be precise. Okay, next we talk about a source of error in numerical method. There are several types of error that can occur, including the first one we call model error. This refers to error that are introduced by using an incorrect or incomplete mathematical model to describe the physical system. For example, a model that measures constant velocity when in reality the velocity is changing will produce an error. And then truncation error. This error refers to errors that occur when approximating a mathematical problems with a simpler one. For example, when approximating a differential equations with a finite difference equations, the truncation error is difference between the exact solution and the approximate solutions. Truncation error is often introduced when using numerical methods such as finite difference and or finite elements methods. And then the last one, we call it roundoff error. This is refers to an error that occurs when representing a number in finite number of digits. For example, representing the number 0.1 as 0.1000000. In computer program, this will produce a roundoff error when the program only stores a first few digits. Roundoff error are result of the fact that computer use finite number of bits to represent the number, and it can occur in any numerical calculations that use floating point arithmetic. It is worth noting that this type of error can be reduced by using more advanced numerical methods and increasing the precision of the computations, but they never be completely eliminated. Okay, next we talk about several numbering systems that being used in the computers. Here are the two most common one. First are binary and the other one are hexadecimal. Binary or the binary numeral systems are base 2 system. It shows only two symbols, 0 and 1, and each digits in binary number represent the power of 2, starting 2 power of point to the power of 0 for the rightmost digit, increasing to the left. So it means that, for example, if you have binary number 0, 1, 0, 1, 1, this will represent 2 to the power of 1 multiplied by 2 to the power of 3, 0 multiplied with 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0. It equals to 8 plus 0 plus 2 plus 1, which equal to 11. And then hexadecimal is the base number of base 16. It's used 16 symbols. The digit 0 from 9, and then the letter A to F. Each digit in a hexadecimal represents a power of 16, starting 16 to the power of 0 for the rightmost digit, and increasing to the left. For example, a number of A3F represent the number of A will be 10. 10 multiplied with 16 to the power of 2 plus 3 multiplied by 16 to the power of 1 plus 15 multiplied by 16 to the power of 0. It means 2560 plus 48 plus 15, it's equal to 26323. Next, hexa is often being used to compute or represent large binary number, and in a more compact and a human readable form. For example, a 32-bit binary number would require 32 digits to represent, while equivalently hexadecimal number would only require 8 digits. In addition, hexadecimal representation is often used in computer science to represent the address of a memory location, and also in a color representation in web development and graphic design. Okay, here's one example of how you can convert a binary to decimals. For example, if you have 1110, it will be equal to 1 multiplied with 2 to the power of 3 plus 1 multiplied by 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 0 multiplied by the power of 0. It's equal to 8 plus 4 plus 2 plus 0, and then it's equal to 14. Next, okay, this one is more interesting a little bit. If you want to convert a decimal to its binary, so you can, there are several way. One of them is this one, forward division. So first you will need to divide the original number 14 divided by 2, because we convert it to the base 2 systems, and then we call it a quotient, means like what will be the multiplicator, so you close to the number of 14, the most close to the to number of 14. So it will be equal 7, because we have 2 multiplied by 7 is equal to 14, and it's very close to the 14. It's even the same, equals, right? And then we need to write the remainder of those divisions. So we have it here 0, because 2 multiplied by 7 is 14, and the remainder is 0. And then you have, like, now you move 7 to be the next number you divide with the 2. 7 divided by 2, and then the closest one would be, if we have 4, we have more than 7, so we cannot use it. So that means the closest one will be 3, because 2 multiplied by 3 is 6. That's the closest one with an integer that we can get to the 7. So, but now we have remainder here, which will be equals to 1, because 7 minus 2 multiplied by 3 is 6. 7 minus 6 is 1. And then you move here the quotient to the front here, and then we still have, we can divide it by 2, which we equal to 1, and then the remainder is 1. Okay, you know how to calculate that one. And then last one here, 1 move here to the new number divided by 2. So the quotient is here, quotient is 0, because if you multiply it by more than 0, you cannot be greater than this number. So you have remainder is equal to 1. Then you can read this one from the bottom here to the top one. Okay, so it will be equal 1, 1, 1, 0 base 2. Then that will be your binary numbers. What about hexa? Hexadecimal, decimal to hexadecimal. It's the same. So you have 147. Instead of divided by 2, now you have to divide it by 16 because hexadecimal is base 16. Okay, 147 divided by 16, you have 9. And then the remainder is 3 because 16 multiplied by 9 is 144. And then 9, you move it here, it's divided by 16, you got 0 here, and then the remainder is 9. Okay, so it means what? It means that the base 16 of 147 is 93. If you want to convert it back, it's the same way with binary systems. You just need to, here, 9 multiplied by 16 to the power of 1 plus 3 multiplied by 16 to the power of 0. Okay, you have here and 147. Okay, this exercise, I think you can do it by yourself. You can stop the video and then start to doing the exercise. And then here's just several theory. We'll read it for you. The floating points and rounding errors. Floating points is a number, is a way to represent a real number in a computer memory. It uses a fixed number of bits to store a value. So, which is typically combination of fractional part and an exponent part. Because the number of bits used to represent the value is finite, it is not possible to represent all real number in floating point. Rounding error occur when value is approximated by a floating point number. Due to limitation of precision of the representations, the result of mathematical operation of floating point number can introduce a rounding error. This can lead to inaccuracy of the final result of a computation. For example, if you add 0.1 to 0.2 together using a floating representation, the result not exactly 0.3, but a close approximation of 0.3. Okay, so be careful with the rounding errors and make sure you understood this floating point. Okay. A roundoff or the rounding of a number, you can use the chopping and roundings. Roundoff error normally occur when a calculation is approximated by a finite number of digits. In most cases, this is necessary because computers use a limitation of bits of represent number. Not all number can be represented exactly. Chopping and rounding are two methods to used to reduce the rounding of error. Chopping is a method of truncation where the least significant digits are removed. This method is simple to implement but cause large error if the number being rounded is close to the next largest representable number. Rounding is a method where the last significant digit is replaced with the nearest representable digit. This method is more accurate than chopping but can still introduce error if the number of being rounded is exactly halfway between two representable numbers. Rounding is the most common method in most of the numerical calculations. It is likely to produce large number of error and preserve more the significant digits. However, in some cases, such as when working with very large and very small numbers, chopping may be more appropriate to method. So here are some examples. You can check this one. How do we do chopping and rounding? And then another things we need to discuss is that when you have a measurements, of course you want to need to understand also what is absolute error and relative error in how to measure the accuracy of measurement of your calculations. Absolute error is difference between the true value of the measurements and the measured value. It is usually represented with the symbols of absolute of the delta, and it is usually measured in the same units as the measurements. For example, if the true value is 10 inches and then the measurement is 9.8, so the absolute error is 0.2. Meanwhile, relative error, in the other hand, is the ratio of the absolute error to the true value. It is usually represented in the delta, the symbol of delta, and then it should measured as a percentage. For example, using the same measurements of the relative error. So before that, we have 0.2 inches divided by the true value 10, and then 0.2 divided by 10, so 0.02 or 2%. Relative error is more useful when comparing the accuracy of different measurements. It is allow easy comparisons of measurements with different unit or different true value. The smaller the relative error, the more the accuracy of the measurement is. It is important to note that the absolute error is independent from the quantity of true value. Wherever the relative error is dependent on the true value. When the true value is close to 0, the relative error will be large even if the absolute is small. Okay, here's this example, you can check that. And then also we talk about error bound. An error bound, also known as a tolerance or an uncertainty, in which is a measure of the maximum deviation of calculated or measured value from true value. It is used to indicate that the level of accuracy of a calculation of a measurements. In numerical method, error bound is often used to estimate the error in a numerical solution of a problem. For example, when solving an equation numerically, an error bound can be used to determine the maximum deviation of the number of solutions from the true solution. There are different ways to compute an error bound depending on the methods used to solve the problems. In some cases, an error bound can be computed analytically by using mathematical properties of the other problems and the algorithm being used. In other cases, an error bound may be determined experimentally by comparing the numerical solutions to known exact solutions by using statistical method to estimate the uncertainty of measurement. The use of error bound is important to know the degree of reliability of the numerical solution. It is also helpful in choosing the appropriate numerical methods for solving problems. It is also important to note that in some cases, the error bound is not known or it is difficult to compute. In this case, the error can be estimated by using other methods, such as comparing the solution to the exact solution or by monitoring the solution changes with the change of the step size. Okay, here is the examples of error bound. And then another concept is that about subtraction of the nearly equals number. Subtraction of nearly equal number is a numerical issue that can arise when subtracting two numbers that are very close to each other in value. This can cause a loss of precision and accuracy result due to the limited precision of floating point arithmetic. The problem occurs because the difference between the two numbers is much smaller than the precision of the representation. For example, two floating point numbers are represented only in 6 decimals digit precision. Subtracting two numbers that differs by less than 1 to the power of minus 6 will not be able to represent exactly in the floating point representation. So a common example of the problems in subtracting two last numbers that are almost equal are subtracting 1 to the power of 20 minus 1 to the power of minus 10. It will result in very small number, but floating point arithmetic, this number will be rounded to 0. To avoid the problem of subtracting nearly equal number, one common solution is to use more accurate representation and numbers such as higher precision floating point or arbitrary precision arithmetic library. Another solution is to a different algorithm that does not involve subtracting nearly equals number. Okay, it is important to be aware of this problem when designing an algorithm and test the implementation with the input are likely encounter this problem. Okay, here's our example, and I guess that will be the end of our discussion. And here's are some reference that you can check if you are interested more on learning about this topic. Okay, thank you very much for listening.